Combustion reaction is a photochemical reaction, an endothermic reaction, an autocatalytic reaction, or an exothermic reaction. Well, most of you got it right. Combustion is an exothermic reaction liberating heat, and that is why we are using combustion in fired heaters, where we are converting the chemical energy in the fuel to thermal energy. So whatever is stored in the fuel as chemical energy, that is released in form of thermal energy via combustion. The combustion process is usually accompanied by well, most of you got it right. Rise in temperature and pressure. I mean, the temperature is rising, and because of the temperature, the pressure also goes up. Thank you. Let's go to the next question. Now, we are all familiar with excess O2 or excess air for completing the combustion. Why do we supply the excess air? Is it for obstruction of inert gas molecules, chemical equilibrium, incomplete mixing of fuel and air, or all of the above? Incomplete mixing of fuel and air is the correct answer. That is why we supply excess air so that all the fuel can burn in the given amount of time. So the other choice would be providing excess fuel and consuming all the air, but that will not be a good efficient choice. Okay, that's an easy one. Combustion is a chemical reaction between fuel and oxygen producing heat. Thank you. Everybody got it right. So you are all combustion engineers. What is stored in fuel? Is it mechanical energy, chemical energy, electrical energy, or thermal energy? So I think we already discussed it. It is the chemical energy which is stored in the fuel, and by process of combustion, we are transferring the chemical energy into thermal energy. So that's what are the three main ingredients for combustion? What do we need for combustion? Thank you. Everybody got it right. Fuel, oxygen, and heat. These are the three things we need to start the combustion. So, but once we have the heat, then the combustion is self-sustaining. And so chemical energy is stored in fuel. This energy is released in the form of thermal energy by fuel. And combustion is central to conversion of chemical energy into thermal energy. And the chemical reaction is taking place between fuel and oxygen. Oxygen, we normally get it from air, and the products of combustion are called flue gases. So fuel and air combust to produce flue gases, and that's the combustion. So combustion has several properties, you can say. First of all, it is a spontaneous reaction. It happens very, very fast. Also, it's an irreversible exothermic reaction because once it starts, you cannot take it back. It has to be uh, uh, keep on going. The reaction time is normally in milliseconds. Especially for the gas components, it's in the milliseconds. It happens very fast. And fuel has three major components: carbon, hydrogen, and sulfur. The first two are desirable components, and the third one is undesirable component. It happens only in small amounts, but it still causes us a lot of pain. And oxygen, we are lucky to get free oxygen from air. So we are not paying for the oxygen. What type of reaction is, I think we already had it, but anyway. Almost everybody got it right. Exothermic. What are the three T's needed for good combustion? I think it should be pretty clear. I mean, the only option with three T's is time, temperature, and turbulence. We need to have good mixing, we need to have right temperature, and then we need to have good timing for mixing. Thank you. So the three T's of combustion, as we call it, is fuel and air mixture needs time to combust. Temperature, that mixture needs to be above the minimum ignition temperature. And turbulence, we need to mix very well. Every fuel gas molecule needs to find the oxygen molecule to have good combustion. So mixing is very, very important in combustion. So here we are talking about minimum ignition temperature. As we said, we need a minimum ignition temperature for any fuel to burn. And that is why we need a source of heat. Now, in most of the burners, we have pilot burner or an ignition torch acting as a source of heat. That's how we supply it. So we need that. Now, another thing which we need to talk about is the flammability limits, because if you just have fuel and air, it is not necessary that they will burn. They need to be in the right proportion. And that proportion is known as between the lower limit is known as LEL and the upper limit is known as UEL, upper explosive limit. So as long as the fuel composition or fuel percentage is between the LEL and UEL, you will have the combustion. If it's below LEL, it will not combust. If it's above UEL, it will not combust. And those of you who are in the operating plants will see how it works out with an explosive meter. So these are the flammability limits for air. The only thing I want to point out in this table is number one, hydrogen. We are all talking of burning hydrogen, but you see hydrogen has the widest range of flammability from 4 to 74%. All the other gases are 5 to 15, 2 to 36, very narrow range for burning. So those are much safer to handle. Hydrogen has a flammability limit from 4 to 74, so it does require special handling. This should be an easy one. How much oxygen percentage by volume is in air? If most of you got it right, 21%. So combustion air is 21% oxygen and 79% nitrogen. Now, nitrogen does not take part in chemical reaction. It is like an inert. It enters the heater at 60 degrees and leaves the stack at 300, 400, 500 and contributing to the heat loss. So our option is minimizing combustion air so that we can reduce the nitrogen volume. That's how we get our efficiency in the heater. Already talked about, sorry, the fuels have two types of heating values. Higher heating value is called HHV, and that is the heat released when we, from the combustion of a fuel, when the combustion starts, combustion is complete, and we condense the water vapor into liquid. So that is the higher heating value, and lower heating value is when we have the water vapor in the vapor phase and it's not included. So basically that's the difference between higher heating value and the lower heating value. So this is a little trick question. I don't know if you know, but what is the lower heating value of methane? If you can guess, that will be really good. Methane is a very clean fuel. It is my favorite fuel. 95% of natural gas is pure methane. Methane also burns the coolest. So I really like it. Well, the correct answer is 900 BTU per cubic feet. I think some of you put 1,000, some of you put 1,100, which was very close. So that's the heating value of methane. This is a chart of heating value. We have the molecular weight of paraffins, hydrocarbons over here, and then we have the heating value on the y-axis. You can see over here the heating value is almost like a proportional straight line actually. The lower one is the lower heating value, the red color is the higher heating value or gross heating value. So that's another thing we want to talk about is the flame temperature. Flame temperature, the adiabatic flame temperature is the temperature which the products of combustion achieve without any heat loss. And you can calculate it by the heat release divided by the weight of combustion products and specific heat. Now, the actual flame temperatures are much lower because they immediately lose heat to the surroundings. So that's one reason why nobody is able to measure the actual flame temperatures. So these are the theoretical flame temperatures, and you can see over here which gas burns the hottest. We have not listed carbon monoxide and acetylene, but they are one of the gases which are burning very hot. But as you can see, most of the flame temperatures are in the range of 3,500 to 4,000 degrees F. That's how hot the flames are. Another thing you want to minimize for efficient combustion is the oxygen content in the flue gas. And this curve shows you the uh, relationship between the oxygen content and the excess air. So if you have 4% oxygen in the flue gas, you are looking at 20% excess air. If you have 6%, then we are looking at 40%. So basically that chart is available at so many places, but it gives you an idea that you need to keep on reducing the excess O2 to get more and more efficient. Uh, what is flame? So flame is a visible part of combustion reaction, and we have a mixture velocity of the fuel gas and air which is coming out of the burner tip. At the same time, we have the flame velocity. And when both match, we have the flames coming out. So that's basically the shape of the flames. If you have a high velocity, the flames may lift up from the tip. Or if you have a low velocity, the flames may start flashing back. So some people talk about color of flames. I don't think that's very important. It basically is depending on how the combustion process is taking place. So here is a poll question for you. What is the thermal efficiency of your fired heater? Uh, well, most of the fired heaters have efficiency between 75 to 85%, and some have even 85 to 90%, and there are maybe cracking furnaces which are in the 90 to 95% range. So pretty good number. So you can see in 1960s, the thermal efficiency was pretty low of the heater, somewhere around 75% was considered good. And then as the oil prices started going up, energy price started going up, and we had the oil price, first oil crisis, and then the second oil crisis. So now we have kind of stabilized at about 94% efficiency. That's typically where we kind of call it, it may go to even higher, but I think that's typically what we are kind of assessing. So why do we don't have a 100% efficient heater? And the reason is we have to have heat loss through the flue gases, and every 35-degree reduction in flue gas temperature increases the efficiency by 1%. And similarly, every 15% reduction in excess air improves the efficiency by 1%. So the stack temperature target, we can go around 200 to 250. This should be 20 degrees centigrade. I think this is wrong, actually, 1.67. We need to fix it. So how low can we go on stack flue gas temperature? All right, we have majority around 300 degrees. Some people can have gone up to 250. Some people want to go to 200 degrees. Let's see if we can successful or 350. So we have a wide range. Now, and this is where the sulfur comes into action. If we don't have any sulfur in the fuel, then the water vapor in the flue gas that will condense depending on the vapor pressure of the water, which could be anywhere 125 to 130. So we can cool up to 130 without this. But what happens is sulfur burns and forms sulfur dioxide, and some part of it gets converted into sulfur trioxide, which reacts with water to make sulfuric acid. And the presence of sulfuric acid raises the acid dew point substantially, almost by 120 degrees or 150 degrees. So once that happens, the sulfuric acid starts condensing and we have corrosion problems. And here you can see the chart of weight percent H2S in the fuel gas, and you can see the dew point is anywhere starting from 240 to 360. So dew point is very, very important. You don't want to get into dew point, and that becomes like a limitation on efficiency. So fortunately, now we are burning clean fuel gases. There is a lot of uh, effort on reducing the sulfur content in the fuel gases. So we can go down as low as possible, and maximize the efficiency. The next is waste heat recovery is very common in cracking and steam methane reformers. So air preheating or steam waste heat recovery are the two ways of maximizing the efficiency. So that kind of completes my training today. If you can provide me some feedback, that will be very, very helpful. Be very honest. This was the first time I used Kahoot. So hopefully I have learned quite a few things. Hopefully we will improve it. And so our plan is to continue this training, even covers cracking heaters and steam methane reformers we want to cover. And our plan is to do one session a month because it takes a lot of preparation to get these slides make. So hopefully, I hope you will continue joining us, and I will start putting the answers to your questions next time. So thank you all for the good feedback.